Hi, I'm Todd Austin. I'm a professor at University of Michigan and also one of the co-founders of Agita Labs, which is a startup that's created a privacy technology called TrustForge. Today, I want to talk about why it's challenging to establish trust in silicon fabrication. Today, the way we manufacture silicon is a company will create a design, put that design into a file, send it to a manufacturing facility, which will then examine that design and then drive their manufacturing capability to produce a chip. One of the challenges of this process is often the company designs the chip in one country and the manufacturing occurs in another country. And those two countries could potentially have different types of government, definitely different laws. So establishing trust between those two international locations can be very challenging. Designers are often worried that somebody might hack into the fabrication facility and modify that manufacturing process to do things like create extra copies of the chip, which can be sold on the black market, or examine those design files and reverse engineer what are the secrets, the trade secrets in that design. Or even worse, they may modify that design to put in a Trojan backdoor that whoever inserted that Trojan can activate later on after the chip has been manufactured. Designers sometimes get so worried about these trust issues that they increase the complexity of their designs, adding things like logic locking and logic camouflaging and reconfigurable logic, essentially bloating the design to provide mechanisms to establish trust in the silicon itself. This isn't a very good approach because it puts the cost of trust on the consumer rather than putting where I believe it should go is on the manufacturer. They should be paying to establish trust. This problem is so great that it's one of the drivers of the U.S. Chips and Science Act that passed in 2022 from Congress, which in part was to bring back silicon manufacturing to U.S. soil to help establish more trust in silicon manufacturing for U.S. chip designers. Well, what I want to show today is that Agita Labs' TrustForge technology can help in this process by essentially allowing zero trust computation at the fabrication facility in a way that prevents stealing of the design. What TrustForge has is two very powerful capabilities. One has the ability to compute directly on encrypted data so that no one at the computation site can see anything about the data or the results of the computation. And it has a safe data release mechanism so that if the agreed upon programs are run on that data, the results, just the results of those programs can be seen. If they're perturbed in any way, changed in any way, there's no output from those programs. This technology has been deployed by Agita Labs in Microsoft Azure and Amazon AWS, and it's programmable with straight existing development DevOps languages like C++, Python, JavaScript. We worked with our partners to do world-class verification of this technology, and as of today, that no vulnerabilities have been detected. And this is really the Swiss Army knife of privacy programming. It can serve many, many different application areas. Today, I'm going to show a demo of it being used to do zero trust computation in a silicon fabrication facility. So when you use TrustForge to do zero trust silicon fabrication, essentially what we're going to do is instead of sending them our design for them to see, we're going to encrypt the design with TrustForge, and we're going to send them just the encrypted design. Then the fab will run TrustForge secure processing, using those capabilities of encrypted computation and safe data release to run their internal algorithms, design checking, mass generation, process control. If they run the approved algorithms that are expected, then each of those will pass muster with TrustForge. TrustForge's cryptographic checking capabilities will ensure that those were produced correctly and release the results of those computations, allowing the manufacturing of that chip. Not the bloated chip, but the original chip that the designer wanted to produce, essentially allowing zero trust computation inside the fab. Now, if somebody hacks into the fab or someone goes rogue on the fab design team, process team, and changes, for example, mass generation to insert a Trojan backdoor into that chip, TrustForge will detect those changes, won't allow that information to be released from those new algorithms, those change algorithms, and the chip cannot be manufactured. This combination of encrypted computation and safe data release essentially allows zero trust processing in the fab. Now, let's take a look at a quick demo showing TrustForge Azure doing what is called optical correction. This is a step in the mass generation process. And during the demo, I'm going to try and insert a Trojan, and it's not going to let me do that. All right, let's get started with the demo. I don't actually run a fab, and I don't have optical mask correction software at my disposal. So what I'm going to use as a proxy for that is fisheye lens correction. So I'm going to take an image, an encrypted image, run it under ZeroTrust TrustForge computation capability, and I'm going to transform it into its linearized, unfisheyed version, defished as it's called. And in particular, I'm going to try and stop the insertion of a Trojan. And here you can see in this example, I've run this output with the Trojan enabled, not on TrustForge. And so inside this window, I've inserted a little smiley face. That's my Trojan. This is actually very similar to how a Trojan would be inserted into a design at a fab. The masks, which are used to generate the chip, are actually optical images, which allow light to pass and then not pass through. And so to insert a Trojan backdoor, you would then have to edit that mask. So it is actually an image editing challenge in the fab. So that's my Trojan that I've inserted into this design. So let's get started with executing some code. So first I'm going to do is I'm just going to build my version of the code that's clean and is what is expected. I'm going to run this on TrustForge. And I'm going to, it's going to do a number of steps. It's going to read the encrypted image, and then it's going to do optical lens correction, and then it's going to do smoothing of the image, which is a computation based on the image data, which is similar to how mass generation works in a fab. And then it writes out the corrected image data. And then I'm going to look at the outputted image data here. And we can see that it is the defished image. And and there's nothing in this window. No one tried to do any nefarious adding of Trojans. Now I'm going to turn on my Trojan. I'm going to go into the code here, and I'm going to turn on my Trojan so that when I rebuild the code, it's going to try and insert this smiley face at specific locations into the code. So this is a programmer that went rogue and has decided I'm going to change this mass generation process. So now I'm going to rebuild my system. I'm going to run it on TrustForge, and it's going to first read the encrypted image. It's going to do mask image correction. And then while it's doing artifact smoothing, it's going to attempt to insert a Trojan into the design. It'll actually run that code to do that. But when it comes time to emit the final result of the program, the data grant, which is called the Sentinel data grant for this particular program, says that the computation that was run does not match the computation of the data grant. Therefore, the hardware will not permit decrypting of these image mask results. So because we changed that code, the cryptographic strength defenses of TrustForge prevent that mask from being generated. And there is no mask output, so there can be no chip manufactured. So this is the advantage of a strong cryptographically secure zero trust computation capability and how it can establish trust in secure trusted fabrication of silicon. All right, I hope you enjoyed that demo. Just a few more pointers if you want to learn more. If you want to learn more about me, please visit my LinkedIn page. If you'd like to learn more about the U.S. Chips and Science Act, you can see the act at this link from the U.S. Congress. To learn more about secure computation in general, you can follow the third link to a class I taught last semester at University of Michigan on privacy technologies. And then finally, to learn more about TrustForge secure computation and how it could perhaps enhance your DevOps to be more privacy oriented, please visit agitalabs.com. Thank you.